So we're going to look at thermodynamically favored reactions, and I want you guys to just jot this down on the side of your notebook somewhere or on your piece of paper. We know that if something is favorable, that it should have these specific conditions. That E cell is going to be positive voltage. You know that delta G needs to be negative, and that K needs to be greater than 1. We all know this, right? So when you start one of these questions today, I say it all the time, be smart before you start. If you get a positive voltage, you should know all of this stuff before you start those problems. And if you're not getting that information correct, then you fix your problem and you try it again. If you get a positive voltage when you have a positive delta G when you have a positive voltage, you know that you did something wrong, right? It's almost like a pre-check. And then non-favorable or non-spontaneous or reactant favored would be that you get a voltage of negative. Your delta G then would be positive, and then your K would be less than 1. And remember that K is equal to products over reactants. So that's all that this is saying here. I already taught you this. You can look at the standard reduction potential table. Instead of using an activity series, we don't use the activity series. We look at the reduction potentials. And then we can determine which one's being oxidized or reduced. And then if we get a positive voltage, that's favorable. So let's look at this reaction. Sometimes questions, they don't give you enough information, right, to tell you if it's one's being oxidized or reduced. And sometimes they don't give you enough information to say that it actually occurs. Sort of like what you did on your quiz yesterday, you had to determine the favorable reaction, which some of you were like a little stressed out about that, trying to figure out what is favorable. The reaction, it says to you, blah, 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 does not occur. So then what does occur? The other one occurs, right? Because we know things like, for example, if I have iron,
Mr. Burns, do you want me to leave?
no, plus oxygen, I get rust, right? This is a favorable reaction. So that delta G means it's negative, doesn't it? That happens. Iron in air rusts. Does rust unrust when you just leave it out? No, that's unfavorable. So if a reaction is negative in one direction, it's going to be positive in the reverse direction. And the same thing is true for your voltages. If it's positive in one direction, it'll be negative in the other direction, because we don't oxidize and reduce at the same time the same substances. One gets oxidized, one gets reduced. So let's take a look at this question. There's two kind of thought processes to doing this. I'll pick one way and then I'll show you what I mean by the other way. But you get a reaction and it's asking you, is this favorable? So like you did yesterday on your quiz, you had to just immediately start calculating values. You had to figure out what the favorable reaction was first. So looking at this information, and then you have your reduction potential list, how are we going to determine what's favorable? So what are you going to do? Calculate your voltage, right? Your voltage will tell you if it's favorable or not. So you have barium sulfate, lead, barium, and then lead sulfate, which looks a little different than what we've done before, but you can still determine what's being oxidized and reduced based on oxidation numbers, right? So if we go here and we say barium sulfate, well, this is barium in the +2 state, it's aqueous. This is 0, this is 0. Lead would be the +2, but it is a solid, right? But that would be its oxidation number. So what should you write down for yourself over here? Barium is what? Being reduced or oxidized? Reduced, right? Because its oxidation number is going down. And then lead is being oxidized because its oxidation number goes up. You know that I'm a huge advocate for writing stuff down before you start thinking through a problem. Because that information, you know how to do that, right? So you don't want to start getting into like part A and part B and part C. You can establish this for yourself early on. All right, so we want to see if this is actually going to occur. So if I said that barium is going to be reduced, then I'm going to use this as my reduction, right? And I told myself that lead's being oxidized, so technically I'm going to flip this because this is the oxidation reaction, and then I'm going to flip my oxidation to be positive 0.13 volts. Agreed? Because I told myself that's what's happening in this reaction. I wrote it out. So then you just calculate your reduction value plus your oxidation value. You throw that into your calculator and you get a negative 2.77 volts. So does this reaction occur? No. What reaction does occur? Can you write that down for me? What reaction occurs? So the favorable reaction should be what? Yeah, the exact opposite of this. So this will occur, but the other way will not. Okay, so this is the correct forward reaction. Good? You didn't write that? What would you have written? Because this is Ba going to 0 plus 2. Go ahead and solve this for yourself. So if this is going from barium to the plus 2 state, then I'm telling myself that barium is oxidized, and then I'm telling myself that lead is reduced. So go and take those values now and make that happen. If barium's being oxidized, then this becomes a positive 0.290 volts, and this stays as the reduction as a negative 0.13 volts.
I did that like now.
There is no net because these are solids. This is a solid. This
I
one
just
is
did,
a solid.
like, you know how you did it down there? I lied.
All that I thought.
Yeah, I didn't think.
Yeah.
So stupid.
All right, so what value do you get here? 2.77 volts positive, so that means that if I do it this way, then it happens, which is the reverse of that reaction written up there. Okay? All right, Gibbs free energy. I really like this equation. You guys will too. It's so easy to use, simple to punch in on your calculator. Your voltage is already easy to calculate, so once you get your voltage, you throw it in here. Really good point is when you take the AP exam and you get an A, B, C part, maybe A asks you for what's happening at the anode, and then B says calculate the voltage. Well, say you calculate the voltage wrong and you get to part C, which says calculate delta G. You always get a point as long as it's consistent with part 2. So say for some reason you messed up on part 2, you'll carry that through in this part and you should get the correct. This is usually, correct answer, this is usually 2 points. So what they will give you 1 point for is the correct number of electrons plugged into the equation. So you have to write this out because otherwise a reader can't see how many electrons you're putting in. And then this is Faraday's constant, which we know is 96,485, and then this is your voltage that you calculated. So if this voltage is positive, which is favorable, that is why the negative sign has to be here. So that negative sign would give you the negative delta G because that's what's favorable when you have a positive voltage, right? That's where the negative sign is useful. The number of electrons that you're going to calculate have to come from the balanced equation and not from a half reaction. Do you understand that? Because if you use electrons from a half reaction, it might be 2 in this one and then 3 in this one. And you might choose incorrectly. So you have to underline this word, balanced chemical equation. Has to be from the balanced equation. All right, so let's just try to use it. Oh, the last thing it says here is that delta G becomes more negative as E becomes more positive, right? As voltage increases, the reaction's more spontaneous, we're going to say, so it's more negative. And then the opposite is true. All right. Find delta G and the equilibrium constant Kc for the following reaction. So I didn't even give you any information about Kc because you already know how to do that from equilibrium, right? So they always couple this with your electrochem questions. They give you electrochem information, then they give you thermodynamics, and then they give you equilibrium all together. So here's our reaction before we start. Here's our reduction potentials that are on your chart. And we're asked to find delta G and K. So you have to start with finding what first. So take your equation sheet out because you need to make sure that you see that these equations are there for you. You don't have to memorize them. And make sure that you know how to use them. All right, so the first thing I have to do is find delta G, but I need to find voltage first. So I'm going to use delta G equals negative NFE. So looking at, this is the reaction that they're giving me. right? I could calculate a voltage that's negative at this point, and then my G would be positive and my K would be less than 1. So I'm just going to go for it. This is what's given to me, so I have to use it. So this is, how do you find what's being oxidized and reduced in order to calculate your voltage? Write your oxidation numbers. That's always the way you're going to figure it out. Or what could you do? If it didn't give me the reaction, it just said I have what was it? I just have chromium and manganese at 2 electrodes. It didn't say which one is where. Then you would look at the table and choose the more positive value, right? But if this is the reaction that it's giving me, I don't just choose randomly the more positive value and say that's being reduced, because it could be a reaction in which the voltage will be negative. Do you follow what I'm saying? Not every reaction they give you is going to be favorable and give you a positive value. So if this is what they give you, you just do it. Okay? So 0, plus 3, plus 2, 0. So manganese, you know I like to write information out. Manganese is what? Oxidized. And then chromium is reduced. So I look for chromium and I say, yep, I'm going to use this one. And manganese is oxidized, so I'm going to cross that out and I'm going to rewrite it right away so that I don't accidentally use it incorrectly later on. And I'm going to switch my voltage to say E ox equals positive 1.18 volts. And then I'm going to solve. So E cell equals the reduction plus the oxidation. All right, so once we find the voltage, now we're just going to plug it into these equations. So this is what I mean by the balanced chemical equation. You have to find how many electrons get transferred. So through the wire, how many electrons are going to go? And so if you do this by half reaction method, and you pick just one of the reactions, you're going to likely choose incorrectly if it's not balanced. So once you balance it, you'll get your reaction, you'll get your electrons correctly. But the easiest thing to do is just look at the charges on both sides. So what's the charge on the left side? Overall charge. It's not plus 3, it's plus 6, right? Because this is a plus 3 and this is a plus 2, which is how you get the coefficients, right? If you wrote out Mn goes to Mn plus 2 electrons, because this is what you will do, and you write out Cr plus 3 electrons, and you go to Cr solid, then you would say, oh, I have to multiply this by 2 and this by 3 so that my electrons will cancel and there's 6 electrons total being transferred, right? That's one technique. The other one is just look at 3 times 2 and 2 times 3, and that's how many electrons are transferred. So now you're just going to throw that into the equation. So negative 6, that's why you write it out, so that an AP reader knows that you know that there's 6 electrons being transferred. So you get 1 point for that, and then you get 1 point for the correct answer. So Faraday's constant, 96,485.
Are we allowed to use 96,500?
No.
Never.
No. On a multiple choice, you're still not going to use that. What are you going to use on a multiple choice? 100,000. All right, so negative 6 times Faraday's constant, 485. And then times my voltage, 0.44. So we're going to end up with joules, and I'm going to show you how you can calculate this with just your units to see what your units end up with. Only an hour and a half to go. Right, the 6 has unlimited sig figs, right, because it's an object. Electrons are actual things, right? So we don't calculate sig figs off of this. And then this one, we're going to have a lot of sig figs here. So we would use 2 sig figs from our 0.44 for voltage. I think I may have a sig fig point on this one, because that's easy to do. So just make sure that you use sig figs correctly. All right, so I just want to show you how you can calculate this. You end up with moles of electrons here, and you multiply it by Faraday's constant, which is a coulomb per mole of electron. And then you multiply that by voltage. Voltage, do you remember, is joules per coulomb? Because we're talking about how much energy is required to kind of pull that electron back from the cathode to the anode. So this is in joules per coulomb. So coulombs cancels, moles of electrons cancel, and I'm left with joules. Got it? And then per mole means for the balanced chemical equation.
What do you
So-
want?
Well, typically we write delta G in kilojoules, but when we get to K, what do you need? So unless the question really says, express your answer for delta G in kilojoules, I would probably just leave it in joules. But it might just say that to make sure you convert to kilojoules and remember to convert back to joules. So you cannot be a joule fool in the next step. So we all are going to really make sure that we can get this K value. You already know how to do it. So you're going to plug in. And here's what I've noticed. In block 2, students that got it wrong, just now, like on this slide specifically, got it wrong because they did not write it out on their paper, and they instead just tried to plug in the numbers in the calculator, and they missed the negatives and they missed parentheses. So always write it out on your paper first. That's where you get points. So we know that Kc is going to be equal to e raised to the negative, and then I'm going to put this all in parentheses, delta G over RT. Right? The negative goes on the outside. Because if delta G is negative, then this overall value becomes positive, and remember that this is 2.7 raised to a big power would give me a K greater than 1. So it needs to be in parentheses. So this would be e to the negative 250,000 joules. I'm going to put this all in parentheses. And then Julia, which R value are you going to use? Why? What does it have to match? You got to know. You know this. It's not pressure. We're looking for joules, right? Because this is in joules. So this is my joule number. This is going to be a joule number 2 per mole Kelvin or whatever that is. And then times my temperature, 298. I meant to put that all in parentheses. Bottom. So I'm going to put like a little dot there for you. And then all of that goes in parentheses. So in your calculator, you should be hitting negative. Sorry, I forgot the negative here. So it should be negative times, and then put your little parentheses, negative 250,000. You can hit divide at that point, and then new parentheses, 8.314 times 298, close parentheses, close parentheses. Did you do that? Did you get it, Julia?
Yeah.
So it is 6.6 times 10 to the 43rd. Thumbs up? So there's like many of you without your thumbs up, so that means you need help.
Not done with it.
If you didn't get it, you need to call me over to your calculator. All right, we are going to do this AP question, which it's an electrolytic cell, and I didn't teach you electrolytic cells yet, but it's not necessary in order for you to do the problem because it tells you exactly what's going on. So we'll take sort of like a 10-15 minute break to do this problem. So come and get it. All right. Under non-standard conditions, what are standard conditions?
1 atmosphere.
One molar. All right. When we have our cell as it operates, right, we typically have in both of these cells 1 molar concentration. So pretend this is happening and this is happening, 1 molar concentrations. Does that say 1 molar?
No.
Because what is this? This is, say, like Y plus 2, and this is Y. The second I start oxidation, what happens to the concentration? Goes up immediately. And what happens to the concentration here? Goes down immediately. So when we say standard conditions, that is momentary. Before the cell begins to operate, that's what the conditions were. The second the cell operates, conditions now change, and we have an increase and decrease in concentration at the opposite electrodes. So non-standard conditions mean that they are not 1 molar, partial pressures are not 1 atmosphere, and the temperature is not 25 degrees C. The concentration of the reactants decrease and the concentration of the products increase as the reaction proceeds. I want to show you what I mean by this. this means like I have y plus x plus 2, and then this is going to y plus 2 plus x solid, right? So if I say the concentration of the reactants decreases, this is the AQ concentration, this is the solid. So this one, the concentration decreases. And then in this one, since this is AQ and this is my solid, this concentration increases. Following that? That's what it's saying if we say the concentration of the reactants decrease and the concentration of the products increase as the reaction proceeds. Concentration is the aqueous portion. Okay? And then it says cell voltage decreases as the concentration of reactants decrease and the concentration of the products increase. So voltage is going to decrease as this progresses because your electrons that are flowing past the point where it's doing its source of power. So like usually we have a light bulb here, okay? As soon as you turn on that cell, the electrons begin flowing through this source and the light bulb lights up. So you guys are in physics, as the current begins to flow and your electrons are not passing that point as fast as they were before, current begins to go down and your voltage goes down, right? So that's what you have to think of voltage. Voltage is just how many electrons are passing this source per unit time. And so they're passing, but as the battery begins to die, it's not passing as often, right? So that's why your toys and stuff start to slow down and they're not working as fast. So electrons immediately begin to flow with giving you a lower voltage. Next slide. So for non-standard conditions, our voltage for our battery might be a 12-volt battery. As soon as you turn that switch on, it immediately begins to decrease in its voltage. So voltage goes down, goes down, goes down until voltage reaches 0, and then the battery is dead, right? So when the battery dies, the system's at equilibrium. That means, like my beaker right here, this is at equilibrium because the reaction stopped, right? It has not changed. I have as much copper as I'm going to make, and I have as many zinc ions as I'm going to make, and voltage, if this were connected to something to read the voltage, would be gone. It'd be 0, and then this is at a state of equilibrium. All agreed? So if voltage is 0, we're at equilibrium. That equilibrium constant would stay the same. So then we can relate this to Le Chatelier's principle. So when we think of Le Chatelier's, you have to understand for this section, this is probably the one question that a lot of students get confused with, maybe answer incorrectly. When you have a forward reaction in Le Chatelier's, and you guys just got your labs back, I can go in reverse of that reaction, right? So if I said, like, here's my reactants and here's my products, if I increase the concentration of this, it drives left, right? We would say that. We don't drive left in a redox reaction. Why? We just did it in the very beginning. It's not favorable. If it's favorable in one direction, it's not favorable in the other direction. Here's the reason why. If we're going from the anode, which is where oxidation takes place, and electrons are flowing this way, right? And they're going down here to the cathode where reduction takes place and the electrons are being accepted. As the electrons flow this way, is it possible for the electrons to flow from the cathode to the anode? No. So you never can go left side favored. You can't shift a reaction left when it's electrochemistry. Write that down. Reactions will not shift in the reverse direction. Reactions will not shift to the left or be reactant favored. Those are all the words we use. I guess it could be reactant favored, but we're not shifting to the left. We're not going to do that. Because electrons will not flow from the cathode to the anode. It's just not going to happen. Cathodes only accept electrons.
What if the anode's on right?
It doesn't matter if it's right or left. I didn't write that. The reaction will be the equation. That's right. That's what I'm saying. This is for the equation. So when you look at an equation and we talk about is it reactant favored or product favored, that's what I'm talking about. So we wouldn't say, according to Le Chatelier's, the reaction shifts to the left because the reaction can't switch the redox. The redox only occurs in one direction. Electrons can only be transferred in one direction. Yeah?
So does that apply to like electrolytic cells too? And stuff? Or are we not there yet?
Electrolytic or not, yeah, it still should apply. Because what we're going to look at is how do we increase voltage of a battery. So we have a battery that's losing voltage. What could we do to increase its voltage? We have a dead battery. How do we recharge that battery? So we have to supply things to it in order to get it to recharge its volts. So here's how you do this. If the system is originally under standard conditions and silver is added. So here's my reaction. I think I want to draw this for you because it helps. Maybe you should draw it for yourself. So we have a salt bridge. Really poor salt bridge here. And we have, let's say this is copper, and it's going to copper +2. And then here's my other electrode, and I have silver, and it's going to solid silver, and then they're clamped together. And then my voltage here is a positive 0.46 volts. I should write E cell. All right. So if this is originally under standard conditions at 1 molar concentration, and I add silver to this piece, so silver's concentration becomes greater than 1. Where is silver on the reactants or product side? It's a reactant, right? If I increase the concentration of reactant, what happens according to Le Chatelier's? It drives where? Drives right, and it'll make more products, which means that this reaction will progress in the forward direction, and the voltage will increase. Voltage, so this is what's really important. Voltage is a product of the forward reaction. So if I'm driving something in the forward direction, if I'm driving this to the right, I'm going to make more product with more volts. Because voltage is because this transfer of electrons from copper to silver, because this is where the electrons are transferring. Maddie, can you help me? Thank you. When electrons transfer, and this is the forward direction, then I get voltage because electrons are transferring, right? Because this is a 0 and this is a +1, so this gets oxidized and this gets reduced. So if that's happening in the forward direction, I get voltage. If I get more electrons to pass that point, my power source up here, then I get more voltage. So I would just then increase one of my reactants, right? If the system is originally under standard conditions and Ag plus is removed, okay, then this causes this reaction, this to go down. So according to Le Chatelier's, you're not going to say this, but you would say it would drive left. But that's why I wrote this, reactions don't shift left. You can't drive the reaction left because redox don't occur in the opposite direction. So what could you say about this? If voltage is a direct product of the forward reaction, but the forward reaction is not going to occur now, it's going to technically slow down because you're removing some of your Ag+. So it would be like, right, we're not going to say it's reactant favored, and we're not going to say it drives left because it can't, but you can think of it like that because your forward reaction decreases, so therefore voltage decreases. So just think of it, what happens to the forward reaction only? So only think what happens to the forward reaction. If forward reaction increases, then voltage increases. If forward reaction decreases, then voltage decreases. That's because electrons aren't being transferred through that wire at that rate anymore. So the electrons slow down, right? They're not going through to that bulb any faster now. Can you see that? Do you want me to read it to you? If forward reaction decreases, then voltage decreases. And that says that here, but in a few bullets. So if voltage decreases, what that means is that the electrons that are flowing through there has decreased. So maybe it was like this, and now it's going like this. Get it? Questions? You're going to get multiple choice questions like this. This is what we're headed towards, is understanding it's going to give you scenarios, and you'll have part A, B, C, D, or 1 and 2 and 3 and 4, and it'll say the voltage goes to 0. The voltage decreases, and then becomes 0. You're going to see a bunch of those questions where you have to decide, according to Le Chatelier's, what will happen. Yep?
So that's how you like charge a battery, you were saying?
There's so many different batteries in what we're doing, but if you had this construction set up, you could recharge a battery by putting in more of a certain substance. You don't do that at home. That's not this type of battery. You don't open up your battery and refill substances, but there are certainly batteries. I'm going to misspeak because I'm only like chemistry, but don't you have to like fix your car battery sometimes and like refill things in there? I think people do that.
Our battery keeps dying, but like we get like jumped or whatever.
Well, you can certainly recharge a battery by jumping. I don't know. I'm sure there are examples that I could think of, but I haven't. But you do sometimes have to refill certain liquids in batteries, and there's certainly cells that use this, but the ones that you're talking about, like your cell phone, it is not obviously recharged by this process. Okay? Lots of other ways to make a battery. But batteries are always made the same way. Electrons have to flow. So this is one way, a redox reaction to make electrons flow. All right, so the last part here is the same thing, but we're just looking about now what happens to our product. So if I add reactants, it drives in the forward. If I remove reactants, it slows down the forward. If I add copper to this, what would normally happen? It would drive left, but we can't say that, so what are we going to say? It slows down, so voltage decreases. Get it? And if I decrease the concentration of this, what happens to the forward reaction? It increases and voltage increases. You can't ever say left and right. You're just going to say, does the forward reaction increase or decrease based on what's according to Le Chatelier's, okay? We're all good? We're going to finish this lecture. Changing concentrations. A cell, originally under standard conditions and functioning according to this equation below, runs until zinc is 1.14 molar. Find what the concentration of gold is. All right, so let me draw this picture for you. We all have this written down? Okay. So I'm just going to change what's in these electrodes. So this one has zinc. I'm going to draw it like this, and I'm going to ask you to determine which one each is. Where's the cathode and anode based on what's written here? All right, well, I'll pick one. Let's say that this is the anode. Well, it has to be the anode. So what am I going to write here?
Yeah, it's oxidized.
I am going to write oxidized, but like, what do I do here?
Zn
plus 2, and then this is Au plus 3. I feel like this is a really important activity for you to be able to do on your own by looking at this, is drawing yourself pictures. Do you see how I came up with this picture? Like, I have to make the electrodes, I have to pick an electrode, and I have to make it make ions or turn into the solid. So using this equation, I'm going to use that information. So what happens to the zinc? It was at standard conditions, which is what? 1.0 molar, and it goes to 1.14 molar. Does that make sense? Because as the reaction progresses, I'm going to make zinc ions, but what's going to happen to the gold? It's going to go away, right? Because you're reducing it so you have fewer gold ions in the solution, right? As my reaction on the bench was progressing, we saw the blue color eventually fade to clear, right? It certainly doesn't look blue at all anymore. Waiting for Kirsten to be like, so the limiting reactant was? All right, so if this is increasing by that amount, then I can figure out how much this decreases by because it's in a mole-to-mole ratio. It is stoichiometry. So this is what you're going to say to yourself. It didn't give me the volume, but I'm going to assume they're out of a 1 liter solution just because ones are easy to use. So if this is a 1.00 molar solution, then I can calculate how many moles I have in 1 liter of this. Okay? So this is 1.14. So I technically have 1.14 moles of zinc plus 2. So I need to know how many moles of gold then are going to be used up in this redox reaction, right? This is supplying the electrons, so 1.14 moles is what's going to end up being made. So I'm going to start this problem with how many moles did this actually increase by? 0.14, right? Because this is minus 0.100 moles. This is what I started with. So I have 0.14 moles of zinc are being made. So how many get used then is just dimensional analysis. So then I look at my balanced chemical equation and I find the zinc and it says 3 moles of Zn plus 2 are going to go to gold, 2 moles of Au plus 3. So you solve for that and you get 0.093 moles of Au plus 3. And then because I did it in 1 liter, I could say that this is 0.0913 moles per 1 liter, which gives me 0.093 molar gold. That's not the answer, though. Why is that not the answer? What is that number? That's the amount that it changes, right? So it was at 1, but what did the question say? It said find the new concentration of this, right? So what are you going to do? If this went away, then this is, we said, this is, I'm sorry, if this is being made, this is the amount that's going away. So do you add or subtract from 1? Because it's going away. So I take my 1.00 molar, and I subtract my 0.093 molar, and I get 0.907. I know, I just wrote the wrong thing. Following? The part that's tricky about this is that you have to recognize, does it go away or does it form? And drawing that picture sort of helps. I mean, it certainly says it there, but I like to see the arrow showing me like this is being made, so it's going to be 1 plus this number. And then this is going away, so it's 1 minus this number. Drawing the picture helps. Good. I'll stop at concentration. I'll do this, but we won't do electrolytic cells today. We'll practice some of the problems before we go. So let's just finish concentration cells. A voltaic cell can function with the same species at the anode and cathode. Okay, so you can literally have the exact same thing, like zinc and zinc, or copper and copper, at one half cell and then the other half cell. So you don't necessarily have to have 2 different things. The only thing you need to do is make them have different concentrations. So most things always go from areas of high concentration to areas of low concentration. Do you remember osmosis from bio? So areas of high concentration to low concentration. Like we think about this like with clouds and weather and how it's like from areas of high whatever to low whatever pressure. They use all these things. So just think high to low, high to low, high to low. So if the concentration is high in one of my cells, then it will eventually reach equilibrium when they have the same exact concentration. So the cell will progress until they have the same concentration. So in order to make a concentration cell, one has to be high and one has to be low. So it says the cell voltage is 0. Why does that make sense? Because your E cell is equal to the E reduction plus the E oxidation. If you're taking one value off of your table, you're reversing one of them, it's going to be 0. Agreed? So it can be positive, though, if the concentration at the anode is less than the concentration at the cathode. So that has to do with like the equilibrium that we were just, Les Chatiers that we were just looking at. So if the concentration at the anode is less, than the concentration at the cathode, that means the concentration at the cathode would be high, we can create some voltage. As the reaction proceeds, the concentration at the anode increases because look, that's what's happening. Concentration needs to increase at the anode. In the aqueous solution, concentration at the anode needs to increase. The concentration will increase and the concentration at the cathode will decrease, won't it? We just learned that. We just drew that picture. So when that happens, you can get voltage because it's going to send electrons to make that happen. But eventually, you'll reach equilibrium when the concentration of the anode is equal to the concentration of the cathode, and then voltage is 0. And then it's at equilibrium. So here's a concentration cell. So what are the same substances there?
Nickel.
So nickel's on one half and then nickel's on the other half, and it produces the same thing, but one gives up electrons and one's accepting the electrons. So it's showing you here, this is the keyword diluted, and the keyword here is concentrated. Because when you write your half reaction, it all just cancels itself out, right? Everything's canceled. But what you can see is that if you're doing the oxidation here and then the reduction here, we would end up with nickel solid, nickel plus 2, and so forth. But this is concentrated and then this is diluted. So then the reaction will occur, electrons will flow, and then we'll be able to get some voltage out of this. I guess the most important thing is just making sure you label and understanding that this concentration, if it's diluted to begin with, will have to increase because oxidation will occur here. And remember, it's not always left to right. All of my slides are left to right, but it could occur anywhere. You're looking for dilution. The one that's diluted will have to increase. The one that's concentrated has to go down. Any questions? Maybe what would be helpful for you is to write out this net ionic equation. Maybe not even net, because things on the left and things on the right will cancel, but can you write the equation? Just write the whole equation for me. You can include electrons of this and this, but use the word diluted and use the word aqueous, and that will help you. Go ahead and write that down. Okay, so because we write out the reaction, and we said earlier that things go from high to low, if this is your high and this is your low, it's going to progress in this forward direction as an increase or decrease, because we don't say it's just going to be favored. Is it going to increase the forward reaction or decrease the forward reaction? It's going to increase the forward reaction. So if I increase the forward reaction, then what happens to my voltage? Voltage goes up. And what were we at before this? We were at 0. So in order to get the voltage to increase at all, we're going up. Agreed? Okay, so concentrated to diluted, we have a concentration cell. That's all for today, and then on Monday we'll do electrolytic, but you're going to solve problems. All right, so for an electrolytic cell, the most important thing, you have your note sheet, right? You're going to write down on your note sheet that electrolytic cells, anytime that you see them, you should know that your voltage will always be negative. Always. So the other way that you'll know it's an electrolytic is it might say to you that a direct current is applied. Or it might say a power source is supplied to this. So if it says that, then you know it's electrolytic. So those are things that you're looking for. It might say to you in the question, a galvanic cell, blah, blah, blah. So then you know voltage is positive. But if it says electrolytic cell, then your voltage always needs to be negative. So if you get a positive voltage, then you've done something wrong, right? So what you're going to do is you're going to have a setup in which the power source is being supplied to your wire, essentially, to get that transfer of electrons. If this is a negative voltage, then delta G is going to end up becoming positive. So it says it requires a source of direct current. The electrodes are immersed into a molten salt or an electrolytic solution. So let's talk about what those mean. Molten means what? Anybody?
Lava.
Okay, like lava. Melted. That's essentially what molten means, is that a solid is at high temperature, enough temperature so that it melts, and it's just the ions that are floating around in ions. Most of the time when we get ions, it's because we put it in water, right? But if I melt something, I just get those as a liquid, and it turns into a liquid, which then I can get ions. So this is a melted solid, which in turn is a liquid. So we can get ions from that. And then an electrolytic solution is just in water, and we get ions from that. So ions and ions are two different sources. It says the anode takes electrons from one species in the solution, which is oxidation, and the cathode gives electrons to another species in the solution, which is the reduction. So we're still going to look at redox reactions, but it's going to be with just one substance. Like before, with a galvanic cell, I would have like a copper electrode and a zinc electrode, but now I'm just going to have a molten liquid. So take a look at some of these. So this is the electrolysis of molten sodium chloride. So I literally melt sodium chloride in this big pot, and then I apply a direct current to it. Electrons flow, then they flow into here and then back out of here into the cathode. So when you have a molten substance, or what we're going to look at in the next one is a solution, okay? If it's molten or a solution, you only get one component, like only one substance, like copper 2 nitrate or magnesium bromide. You'll get one thing, sodium chloride. So you have to choose. So the first thing that you should always do is write the reaction that produces ions. All right, so here's my reaction, sodium chloride. That's going to be molten. It's a liquid. And it's going to produce Na plus ions and chloride ions. Do we agree? All right, so now you have to choose.
We're entering a code white. I repeat, we are entering a code white. Thank you.
It's called snow.
Okay. So you have two ions here. So think about this. There's nothing else that can be oxidized or reduced, but yet we're having a redox reaction. So your choices are, does this get oxidized or reduced, or does this get oxidized or reduced? And you just have to be smart about this. We're not going to memorize it. We're just going to think about, what does oxidation and reduction mean? Leo says Gur. So if I'm gaining electrons, I will be reducing. I will lower my oxidation number. Does this get oxidized or reduced? Reduced. What if I oxidize this? What happens to its oxidation number? It would go up. Do I get Na plus 2 ever? Just think about that in terms of like everything you know. You would never write Na plus 2, ever. So don't do that. You could memorize, certainly, that the cation is going to get reduced always, and that the anion is always going to be oxidized, but just think about that in terms of common sense. So my choices are that Na plus is going to have to get reduced to become sodium, and that Cl minus is going to have to become oxidized, and what happens when chlorine becomes by itself, or goes diatomic? And then I'm going to lose the electrons here. So let's balance that for 2 electrons there. So you have to recognize what gets oxidized and what gets reduced when you do this. Okay, so I'm going to write that down. The metal cation gets reduced, and the non-metal anion gets oxidized. That's always going to be the case, right? When we did our our last homework questions where we had to underline what gets oxidized, what gets reduced, that was sort of prepping you for what's happening right now. That should just make sense to you. So when we have this set up here, where I have sodium chloride that's molten, I end up with the oxidation and reduction. And so let's just look at, if they didn't tell us what was happening, could we determine that from this slide? If they didn't label the cathode and the anode for us with the reactions, would you be able to identify them? What's your clue? Okay, so I already identified what's oxidized and reduced. How do I label my anode and cathode if it wasn't labeled for me? What is the clue on here? The bubbles, right? Because you're making chlorine gas. Get it? What if there was if I was making bromine, bromine's a liquid, iodine's a solid at room temperature, so maybe they would show you some solid pieces. They sometimes give you clues at the electrode, at the site of where it's occurring. So you would then be able to label this as the oxidation, as the anode on this side, if they didn't give it to you. Is that clear? Okay. All right, so this is a molten.
This concludes the code white. Repeat, this concludes the code white. Thank you.
All right, this next slide, this is where we're going to spend almost all of our time. So don't look at the slide yet. Just listen to me, and we're going to write a bunch of stuff down. So we could have sodium chloride going into water, or we could have it by itself. You could have this with any ionic compound. It has to be an ionic compound because if it's not, you're not making ions, right? If you don't make ions, you can't have reduction or oxidation. So it's always going to be a salt by itself, molten, or a salt in water. Those are your choices. So this is your molten choice. Molten salt. Okay, label that here. The next one we're going to do is an aqueous salt. If we have an aqueous salt, somebody erase this now. If we have an aqueous salt, we have to make choices between what gets oxidized and reduced. So an aqueous salt is in water. All right, sometimes, and today's a good example, we can really relate this reaction to stuff that you have in your everyday life. So one of the things, and I had it, but my husband must have taken it back, was an actual chlorine generator. So we've talked about pool chemistry probably a lot in this class because that's his field. So his company makes a chlorine generator, and the chlorine generator literally does electrolysis in your saltwater pool. So some people think that they're swimming in a saltwater pool because it makes their skin feel soft, they can open their eyes, there's lots of reasons why they think it's better. But the reason why you have a saltwater pool is so that you don't have to walk to your shed and dump a whole lot of chlorine in your pool all the time, because they're doing an electrolysis, cell is reacting and creating the chlorine that the pool needs. So when you have salts in your pool, right, we have Na plus and Cl minus, we just looked at that reaction, you're generating chlorine, right? Which there's a few more reactions involved, but there's a possibility that there are more ions floating around in your pool water that could be oxidized or reduced, right? And in this example, which is a very basic one, we can choose either the metal or the non-metal for oxidation and reduction, but you can also choose water as being an oxidation or reduction site. And then in addition to that, if there's any other metals in your pool water or non-metals, any ions floating around, those become a choice of oxidation and reduction. Like if I have a cell that's set up, here it is, it's on a piece of wood, posted, and here's inside is my cell occurring, and I send the pool water through it and it comes back out. This doesn't say, all right, I'm only looking for chlorine, only chlorine can come through. It looks at everything, and then our reduction potential list tells us which one's going to get oxidized and reduced, right? Like nature decides that. There's other ways you could set this up to kind of perfect it, but you realize that the reduction potential list, which is essentially an activity series, tells us who gets oxidized and reduced. So you could get a whole list of choices, and then you just go through your reduction potential list to pick which one gets oxidized and reduced. For our purposes, pretty much these questions are always the same. You will always get 4 choices. You'll get one as the metal being reduced or water being reduced, and then the other one is going to be the non-metal being oxidized or water being oxidized, because you have to choose if it's in water. So if it's an aqueous salt in water, this is what you're going to write. You have 4 choices. It's going to be the metal cation or water. These are your reduction choices. So choice 1 or choice 2 for reduction. Your next choice is oxidation. So choice 1 is the non-metal anion. And your choice 2, again, is going to be water. Those are always your 2 choices. So how do you know you have to choose with water? It will say an aqueous solution. How do you know you don't choose with water? It says it's a molten solution. right? Not solution, a molten liquid. So what you'll have to do is take your reduction potentialists out just for our purposes, but you know now on the exam you don't get this, right? So then how will you choose? They're going to give it to you in a table of 4. That's what they do. So they show you the water, and then they show you the metal and the nonmetal, and then you just simply choose between the 4 which gets oxidized and reduced. This is tricky, so get your thinking cap on and ask me questions if you get confused. You all have to understand this or there's no way you're doing it. You can't go home tonight if you can't follow this. Ready? Look at this sheet. You'll always be able to find your metal and your nonmetal. Do you agree? And we all understood early on how you can choose that the metal gets reduced because it's the plus one, it's the cation. So that one has to get reduced, and then the nonmetal has to be the one that gets oxidized. So when you go to look for it, you find it, and then you flip your reaction. Agreed? Okay. How do you choose which one is the water reduction and which one's the water oxidation? Look at your list. You have 2 waters on there. So 5 down. Do you see 5 down? It says O2 plus 4H plus 4 electrons equals 2 waters, or produces 2 waters. So if you get that reaction, is that an oxidation or is that a reduction of water? Oxidation. Because water has to be your reactant. So you need to write that down. Key thing when choosing between these 2, water has to be a reactant. Then determine where the electrons are. So if the electrons are going to be as a product, then that would be oxidation, right? If the electrons are part of the reactants, then that's a reduction. So once you make water be the reactant, then examine electrons, or where electrons are located, to determine if it is oxidized or reduced. All right, so looking again at the 5th one down. Water in this case is a product, right? So in your mind, flip that, because I want it to be a reactant always, because water is what's in your swimming pool, right? So if I'm choosing that, or if I have an aqueous solution, water is what's in that beaker. So look at that reaction, flip it in your head. Where are the electrons located? On the right, which means that they're giving them up, which is oxidation. Do you understand that? Go down the page, find the reduction of water. Did you find the reduction? Where is it? Like 3/4 of the way down?
Yeah.
So it should say 2H2O plus 2 electrons yields H2 plus 2OH minus. Water is a reactant at that point, correct? So then if you see the electrons are being reduced because they're gaining them, right? Leo says GER, gaining electrons is reduction. If it's gaining them, then that's the reduction. Okay, so now I have 2 choices. The metal cation or water, or the nonmetal anion of water. You see how water can play both roles. All right, so now we're going to solve this problem. Really, all you're going to do is eventually calculate voltage, but you have to make the choices first. So let's take this problem. Aqueous calcium iodide. What's the first thing that you have to do? I wrote it early on. Always for all of them. Write your reaction. What I mean by your reaction is take the component that it gives you, whatever substance, and dissociate it into its ions. So if you don't understand what the word write the reaction means, write on your little notes right now, dissociate into ions. That's what we're doing. So I'm going to dissociate this into the ions that would form. Anybody need help with that? We're good? All right, so can I erase this? We have this written down? I'll erase just this part. Gracias. All right, so I have calcium and I have iodine, and I'm going to tell myself right off the bat which one's being oxidized and which is reduced. So what does calcium do? Just think about oxidation number. This is a +2. I'm not going to a +3. I'm going to go to a 0, so it has to be reduced. So write for yourself, just like they do here in the slide, you give yourself the choice, reduced. And then you write choice 1 is Ca +2 plus 2 electrons yields Ca solid. And then the voltage is right there for us as the reduction. So that's negative 2.87 volts. But you have to now put water in, right? That's what I wrote right here. The metal cation and then water. So now you go and look up on your reduction potential list, or if they give you the list of 4 of them, you pick the reduction of water. And you do that by making sure the electrons are on which side? The left side. So here is the reduction of water because electrons have to be on the left side. So 2H2O plus 2 electrons yields H2 plus 2OH. And the voltage there is negative 0.83 volts. So when it goes through my electrolysis cell, which one does my electrolysis cell reduce? Always the same rule. When choosing which one gets reduced, it's always the most positive. Which one's more positive? The second one. So this becomes the reduction. Right? Which is what this says here, is that this gets reduced, right? So I made that choice by looking at those reductions. All right, the next part's going to be a little tricky for you to follow. This is how I do it. You could do it your own way, a different way, but I do it this way to make sure that I don't get confused. Because I always want to choose that my reduction potentials, I always choose my most positive gets reduced. That's really easy to stick with. Because if I start thinking like the most negative gets oxidized and then I'm flipping things, then my negatives and positives get confusing to me and I can't pick the right one. Me personally, that's how I would work. So I'm going to always stick with the most positive gets reduced. So now I'm going to flip this and I'm going to find my oxidation reactions. So on my piece of paper, I would write, if I'm solving a problem, which ones are oxidized. So I already know that my I minus is going to go to I2, and it's going to be 2 electrons because we have to balance for the 2 here, right? That's the oxidation. And then I'm going to go choose the oxidation of water. So I go look up on the chart, and I make sure that water is a reactant and that electrons are on which side? On the right side. They have to be if they're in oxidation. So I'm going to write 2H2O yields O2 plus 4H plus 4 electrons. Okay, at this point, notice that when I wrote this for myself, I did not write the voltages. I just wrote the oxidation reactions, okay? Because I'm still going to choose which one gets reduced, even though I'm looking for which one gets oxidized, right? Because I just explained that my brain works better if I keep things all the same. So when I go look up those values on the table, this is what they are. These say reduction, reduction. Circle those on your notes so that you don't think that they're giving you the wrong value. They're giving you the reduction values. I'm sticking with the reduction values right now. Can you grab the door? Sorry. So when you examine the reduction values, you choose the more positive, and that one will tell you which one is being reduced. So looking at these values, which one's more positive? The water is more positive, so that means it gets reduced. But what do I want? I want to know which one's being oxidized. I don't care which one's being reduced, so by default, this one must be the one that's getting oxidized. Do you see how you choose? That works for me. If you want to go figure out a different way to do it, go for it. But I don't flip my numbers until I choose which one gets oxidized. Then I will tell myself, all right, I just said that iodine's going to get oxidized, so now at this point I will write the word E-ox, so I don't screw it up, and I write negative 0.53 volts. Got it? That's why labeling your oxidations and your reductions and all that is really important. Questions at this point? Yeah.
I'm still confused about the two waters.
Okay. So water always has to be a reactant. In both of these cases, water is a reactant because it's already flipped for me.
Okay.
The way you know which one's being oxidized and reduced is based on Leo says Ger. So if your electrons are being lost, that's oxidation. So where should the electrons be? Left side or right side? Lost electrons.
Yeah, on the right.
Yes. So that's what you're looking for. This one has electrons on the left. This one has electrons on the right.
Gotcha.
So as a-
the electrons.
Yes, but only once you make water a reactant. Because if you look on the chart, and if you get like an AP question is always going to give you the reductions. So it's going to flip this one because this is a reduction if I flip it. So the chart will always give you the reductions just like your chart does. So then you have to recognize water has to be the reactant, and if it's not, I'm going to flip it and then I'm going to examine the electrons.
Gotcha.
That's the hardest part. And then the second hardest part is once you flip those oxidations, to not flip the numbers, choose which one gets reduced first. By default, the other gets oxidized. And since you're looking for an oxidation, you're going to choose the other one. That's how I would do it. All right, so now I can calculate my voltage. Which should it be? Positive or negative? Negative, because these are electrolytic cells. So an electrolytic cell should always be negative. So at this point now, I'm going to take my negative 0.83 plus, what is it? Negative 0.53. Because we flipped it since we're taking the oxidation. It's rough. How do you get good at something?
Practice.
Got it? So let's try another one. So this is just showing you the picture of what's happening. Same thing as before. We have bubbles occurring on one end because the reduction of water, we have bubbling occurring. And then on the other side, we have solid being produced, which this is trying to make it look like it's colored. Like the solid iodine is actually colored. What color is iodine, by the way?
Blue.
It has like a bluish color, but then when doctors scrub in, it looks yellow. Like iodine and iodide have distinctive colors. So that's what they're trying to show you here. But whether or not you see the yellow on an exam, I'm not sure that they would actually do that. They wouldn't, because it's always printed in black and white. All right, so here's the question. Let's see if you can get through it all. This is exactly how it would appear on an exam. Sort of like the question that I gave you for, we did it all in class. Remember this question? We did in class. See how they just gave you the table? They'll do that, but with 4 of them. So now we have to go through this and analyze it. We don't need our own reduction potential list. We can use the one that's given here. All right, step 1, always. For anything, molten or solution, what do you do? Write your reaction. So it says a direct current is applied to an aqueous copper 2 bromide. What should the voltage be? Because it says direct current, right? So electrolytic. So copper 2 bromide is this, and I'm going to write the dissociation of the ions. Do you agree? If you don't know what I mean by write the reaction, this is what I mean. Write the ions. All right, now it says, what is the reduction half reaction? So I have to set this up with 2 choices for reduction and 2 choices for oxidation. I just want to be clear at this point, if they wanted to challenge you even more, they could give you 3. They could say copper 2 bromide and sodium chloride solution are mixed, write the reduction half reaction. So at that point, you would take the copper, you would take the sodium, and the water. And then you would choose which one gets reduced out of those 3. That's not much harder. It's just more work, right? You could have any number of choices. You're always going to choose the more positive to be reduced. All right, so let's write that. The reduction. I'm going to do it on the board. I'm going to leave this all up so I can keep the numbers. Otherwise, I'll have to keep flipping back and forth. But you can go onto your slides where there's empty space, okay? So for the reduction first, I have to look at this and make a choice. Who's going to get reduced? Think about it. If you want to say that this gets reduced, bromine gets reduced, then what would its charge become if you reduced it? Think about that. Br minus 2. We don't have Br minus 2. Right? So if you accidentally choose the wrong thing, just think, well, what would that become? And then say, oh, well, that doesn't make sense, so let me choose the other one. So my first choice, is that it? Oh. Okay. You cannot probably get through it. You could try it. Evens, if you can. You definitely, we're just not going to light it. I'm just not going to light it. What?
This is so weird.
I'm the one in the middle of OCD.
Hello.
I'm turning 7, guys.
Oh my god, it's recording! Wait, turn it sideways.
Trying. Chloe and Maddie, you gotta get in if we're
What do you want me to do?
On lift rock.
Sorry.
Alright, I'm gonna squat so I don't look that.
Yeah, JC, what?
Oh my god, JC looks their whole life.
We don't want to.
It's so big in the
all
camera.
in there?
Yeah.
Alright, we set a 10-second timer.
Yeah. Alright, Mr. Bruin, you gotta run.
Where's Mr. Burn going?
Everyone squish! Kristen, you're not in the camera.
Yo, someone get for JC. PC doesn't get in.
Alright, 3, 2, 1.
Happy
birthday to you. Happy birthday to you.
Are we getting in?
Happy birthday, dear JC. Happy birthday to you.
Wait, hold that for 10 seseconds because
get on
we're still
video?
on 10 seconds.
I did.
Wait a second, I got it on off. Okay, happy birthday to you. Pretend. Blow!
JC, you want to spit on the cake?
Yeah.
Yeah, JC, why don't you spit on it?
I just spit all
Thanks, Mom. Thanks, Mom.
Okay.
Alright.
Yay!
Stoic.
Now I'll turn on the projector.
Goodbye, everyone. Go see how good our class is.
So, electrolysis, we're back at this question from yesterday, and I'm going to leave this up, and you're going to write your reactions on the other slides, right? So we get through B? Okay, someone answer. We didn't start any of it. Okay. So remember that you always have two choices. You will have your copper 2 bromide solution. So when I write copper 2 bromide, I'm going to write Cu plus 2 plus Br minus. Remember I said always write out your dissociation reaction first. So CrBr2 gives me this. Do we all agree? So I have two choices. Copper is going to be reduced or water is going to be reduced. And then bromine is going to be oxidized or water is going to be oxidized. So that's why you have 4 reduction potentials right here. And then you're going to solve for which one's going to be reduced based on the more positive value. So what I would do is I would write down, since the question is asking for the reduction, I would write down both of my choices. Choice 1, this can't be oxidized. Why not? It's already at its max plus 2 state, right? So we're just going to, you just recognize this one has to be reduced. So Cu plus 2 electrons gives me Cu solid. And then my other choice is the reduction of water. So you go and look. And what does water always have to be? A reactant. So water here is a product. Water here is a reactant. I need water to be the reactant, and I need electrons for the reduction to be where? If something's being reduced, where do electrons need to be? On the left, always, right? So if I flip this one, electrons would be on the right. Do you see that? So this is not the reduction, this is the oxidation. So this is the reduction of water. So I'm going to write that one out. This is 2H2O plus 2 electrons yields H2 plus 2OH minus. So now I choose between these two. Which one is going to get reduced? This is negative 0.83 volts, and then this one is, just joking, 0.34 volts. And then that one is negative, where am I? Negative 0.83 volts. So the more positive value is going to get reduced. This is more positive? Yes? So then this is my reduction reaction. and I ignore the other one. So this is the reduction. I don't mind if on my test you do out your work like I am and then square it or something and then tell me that that's the reduced one. Okay? All right, so the next part says, what is the oxidation half reaction? So I'm going to do the same thing. Part 1. I'm going to write down my two choices. I have bromine going to Br2 plus it'll be 2 electrons in order for me to balance that, right? And then my other choice for oxidation is water, which is when water is a reactant, which it will be, the electrons need to be on the right side for this reaction. So remember I said I already write out the oxidation reactions and I don't worry about their values yet. I'm not going to write their values down. I'm going to go look at the actual reduction values given here. So this one and then this one. These are my two choices for oxidation. But I'm going to look at the reduction values to choose which one would get reduced. Which one would get reduced? This one. The water would get reduced. But I'm looking for the oxidation reaction, so which one gets oxidized? The other one. Okay? If you don't like that technique, you try like 5 problems on your own and figure out a technique that you do like. But this is how I like to do it. And there's definitely different thought processes. I don't mind that. You just have to come up with the right answer. So if this one is the one that's going to get reduced, I tell myself that, oxidized, this one gets oxidized because the other one gets reduced. Good? All right, so then the next part says, what is the overall reaction? Oop. I thought I just paused that. I'm on the wrong computer. Oh, boy. Sorry.
I just realized you have 2 MacBooks.
I do, which is why I accidentally go between them.
Are like one of them yours actually?
None of them are mine, but all of them are. They all come home with me. Well, sometimes. All right, so we already got here. We chose those values. So our overall net ionic then is this plus this, and then we balance for the electrons. So the electrons will cancel. Agreed? Any questions with this? All right, the next part is asking me to find delta G. I'll wait till you catch up. All right, so now we're going to find delta G. The only equation that you can use for delta G, and I guess I gave a different free response out where I asked students to calculate delta G. The only information that was given was the voltage. You can't use the equilibrium. Remember we did equilibrium though with this? Like we solved for voltage, we solved for delta G, and then we solved for K? Yes? We can't find K at this point. We can't use that negative RT ln K equation because we don't have K. The only equation that you possibly could use at this point is negative NFE because we can calculate voltage. So we're going to throw this in. We have to first calculate voltage given this reaction. So if this is my reduction reaction here, that's positive. So we're going to do E cell is equal to the E reduction plus the E oxidation. The reduction reaction is the positive 0.34 volts. We go back and we look at what was the reduction potential for the oxidation reaction. Go back and look at it. What? 4.07? 1.07, so then I have to do what? Flip it. So I have to get negative 0.107. So minus 1.07 volts, and I get a negative 0.73 volts. Does that make sense? Yes, because it's an electrolytic cell. If you don't get a negative voltage, then you've done something wrong. What should delta G be? Positive. So now we have to throw this into our negative NFE. What does N stand for? Moles of electrons transferred, not moles of anything else. So how many electrons got transferred in our overall reaction? 2, right? Because there was 2 transferred here and 2 transferred here. If it was 3 and 2, then it would be 6. You would use least common multiple. But this is going to be negative 2 times Faraday's constant, 96,485, times my voltage, 0.73, which is negative. The negative and the negative will give you your positive to give you your delta G. You check your work by understanding the positive and the negatives. Yep.
Can you go back one slide? I have a question. What do they mean, like the heat reduction and oxidation?
That's how they, remember I told you don't do it that way. Yeah. Like it's basically telling you to flip it, but you already know it's E reduction plus E oxidation, and you know to flip it when you're looking at the oxidation number. It's just, every single time you see this, just cross it out. Because I don't do it that way. Yep.
When you used it, like on the board, it said like 98,500. You still want to do the 98,455.
Yep. If it's free response, you have to use the numbers supplied by the AP exam. Okay. Last part, and then we'll just practice these. It's just showing you how we're going to end up using dimensional analysis to calculate those masses. So this says metals can be refined through electrolysis. In the previous example, solid copper was plated out on the cathode. This is really relevant. Like companies make a living out of doing this, and some very wealthy companies, not many people are involved in like the metal refinement business, but you know that people recycle metals, right? So then what do you do with those metals? You throw them into a huge refinery and you get out new metals, essentially old metals, but they're refined now. They've taken out all the excess stuff on them or the other components, and then they refine metals, and then they resell you what you just recycled, or they resell it to somebody else. So that's a really big business because basically there's just garbage is what you're collecting, and then you're refining it into metals. So the way that they do that, besides the fact that you could use, and we talked about thermodynamically, like heating stuff up to drive off like an oxide or something like that, or a nitride, you can do this through electrolysis and metal refinement. So say I have two different components like copper 2 bromide, I can use the electrolysis and come up with just plain copper, and then I can sell you copper. So we're going to calculate how long it will take to get a certain amount of copper. So how long would it take to plate out 3.56 grams of silver from a solution containing silver plus 1 ions with a current of 2.5 amps? So right away, if I give you amps, what do you do? Coulombs over seconds. So we're not even going to like think about the problem for a second. We're just going to remember that Mrs. DeBruin said to change that. All right, the second thing that you need to do for these reactions, always, we did them in the very beginning with lecture 1, you have to have a reaction. So write for yourself, step 1, always write the reaction. Otherwise, you can't figure out anything about moles of electrons or your mass with stoichiometry. So what is the reaction? I have silver from silver plus 1. So how long would it take to plate out silver, so solid silver's over here, from silver ions, Ag plus 1 electron. All right, so this is my stoichiometry for 1 mole of electrons is to 1 mole of solid. So I'm going to start with my known, which is 3.56 grams of silver. That's what it's asking me, and I want to get to time. It's going to be a massive dimensional analysis problem. So I'm going to go and convert from grams of silver to moles of silver. Where do I find grams to moles? On the periodic table, so you go look up silver. Is it like 127?
107.
Oh, I was off. 107.87?
Yeah.
Is to 1 mole. And then I'm going to go from 1 mole of solid silver. And the reason why I'm going to electrons here is because the only other conversion factor that I can use is 96,485 coulombs is per 1 mole of electrons, right? So I'm going to use that here, so I'm going to go to 1 mole of electrons. And then from here, I'm going to go from 1 mole of electrons to coulombs, Faraday's constant, 96,485 coulombs. And then I'm going to use my amp, which is 2.5 coulombs, is to 1 second. And that's how I can figure out seconds. If it asked me to figure out minutes, then I would convert to minutes. and so forth. I promise you I'm giving you this on your exam. Do you hear me? Promised. And as a multiple choice also.
What if
What?
it was 2? Like,
2 moles of electrons?
yeah.
Then you put 2.
You just put 2.
Yeah, we did this. We did this already once before where it was more than 1.
And then like, there would only be 2 moles of electrons. It was like Ag plus 2 electrons.
Yeah,
What was
it would be Ag plus 2 electrons, right? Like Zn plus 2 electrons. All right, so then you're going to calculate. Yes?
For and will they ever put it over like 2 seconds or is it always 1 second? So I know the conversion
1
back-
second.
Oh, you forgot 1%.
Well, it didn't say. I wasn't sure what it was asking me for. How long means whatever you, but they would be more specific. So this question says like how many minutes. So then we would do 60 seconds equals 1 minute. So then the answer right here is 21 minutes. See?
Does the coulomb count as like the 2.5 coulombs? Does that count as?
As a sig fig? That one does. Yep. What doesn't count as sig figs are something like conversion factors like this, 1 minute equals 60 seconds, or like moles of electrons. Those are actual objects. We don't count them. Okay? You have a whole bunch of these in your homework to try. All right, this one says if 2.0 Faradays of electric charge pass through a silver nitrate solution, what mass of silver is plated out? So what did I just write on the last side? First step, always write the reaction. So I'm going to say silver nitrate. Nitrates are soluble. What mass of silver solid is plated out from this reaction? Same thing. So if I'm starting with 2.0 Faradays, how many silver grams will I make? So watch. What is a Faraday? Yeah, but I can't use Faradays. I can just use like moles of electrons or coulombs. So Faraday's constant is 96,485 coulombs per mole of electrons. So wait a second. I want you to convert the word Faraday to a coulomb per mole of electron. Do I? Yes. Let me just look at my note, what I wanted you to do. Right, that's the first part. I need you to convert Faradays. I wrote over it. I need you to convert Faradays to a coulomb. So if a Faraday is 96,485 coulombs per mole electron, that's 1 Faraday. So what I can say is in 1 Faraday, kind of like a ratio, if I have 2.0 Faradays, that's equal to 1 Faraday per 96,485 is to how many coulombs here. So all you do is when you have a Faraday, you multiply it by the coulombs. Got it? So this is 2 Faradays. So how many coulombs is that technically? Like 1 Faraday is 96,485, so 2 Faradays would be double that. Do you agree?
So Faraday's another word for multiple electron?
Kind of. So look, we're just going to calculate how many coulombs here. We're not going to calculate it yet. We're going to do dimensional analysis. Then watch. Then I'm going to say 96,000. I'm going to keep it here. 500 coulombs is to 1 mole of electrons. You're going to get this as a multiple choice problem. And the reason why it's easy is because you end up canceling this out. Do you see that? It's anytime they give you a Faraday, you're going to multiply it by Faraday's constant to figure out how many Faradays you have essentially, or how many coulombs you have for your Faraday's constant, and then you're going to finish the dimensional analysis as if you were starting with a coulomb. So coulomb, coulomb. Get it? Yes?
So do you have to put the, like that one where you're multiplying it, you multiply it by the C, but do you have to put it over a mole of electron?
We are here. We're not putting it over 1 mole of electrons here. Because at this point, we're going to cancel it out by doing 1 mole of electron of the silver is to 1 mole of Ag. And then 1 mole of Ag is equal to that 107.87 grams. And that's how we'll solve. So look, if you were doing this without a calculator, how easy is this now? No calculator. You're just taking, essentially, these cancel. 2 times 107 or 108. There's your answer. So these will be given to you as multiple choice. So anytime you see Faraday, you multiply it by the coulomb. That's what we did here. 2 Faradays times 96,485 coulombs. Good?
How many sig figs would we use there?
So for sig figs, your 2.0 Faradays, I would say from that you would take it.
So it'd be like
Yeah, I mean, these are going to be multiple choice questions always. The one that I just gave you before this slide, that's where you end up with a free response. I would say I would round that to 220 because the Faraday is an actual measurement, and that's 2 sig figs, so then I would stick with the 2 sig figs for that. All right, so you're going to finish homework.